Welcome to the Astro Guy podcast. I'm your host, Wayne Zool. When I mention certain terms or concepts in an episode, I often worry that people, especially beginners, may not understand them. So to make the amazing hobby of amateur astronomy just a little bit easier to understand, let's examine some of these terms and concepts together. One of the most misunderstood concepts in astronomy is angular measurement, so let's start there. Angular measurement is a useful way to explain the sizes that things appear to us, as opposed to how large they actually are. For example, we know what the actual diameter of Jupiter is. It measures 88,846 miles in diameter. But when we see it with the naked eye, it only appears as a bright point of light. Because it's so far away, it appears small. Like when you're driving on a highway and you see a mountain in the distance, it looks small, but when you finally get there, it's huge. Well, Jupiter is huge. It's more than 11 times wider than the Earth, but at an average distance of 400 million miles from us, Jupiter appears nearly like another star in the sky. So describing it to a viewer as being 88,846 miles wide is interesting, but it's not useful if you're comparing it to a galaxy, for example, that Jupiter will appear near in the sky. I wouldn't say sweep 400 million miles to Jupiter and notice the galaxy 10 million light years to Jupiter's east. That makes no sense to an observer at the eyepiece. So, how do we handle it? Well, we use angular measurement to describe the diameter of the objects that we see in the sky, as well as the distances from one spot in the sky to another. Picture the sky as a dome that spans 180 degrees from horizon to horizon. Looking at the horizon in front of you would be 0 degrees, while looking straight overhead would be 90 degrees, and halfway would be 45. If you had a sextant, you could look at the moon and measure that it's about half a degree wide. But not everyone has a sextant lying around to take angular measurements. Fortunately for us, there are ways to make some basic angular measurements using your hand held at arm's length. Make a fist and hold it out in front of you at arm's length. Now extend your pinky. The width of your pinky at this distance is about 1 degree wide. Again, make a fist and extend your first 3 fingers. The width of your 3 fingers is about 5 degrees. Now close your fist, and the width of your fist is now about 10 degrees wide. If you extend your pinky and thumb as wide as they'll span about 25 degrees wide. So now, if I were to tell you that at 9 p.m. on Tuesday, the moon will be due east and be 10 degrees above the horizon, you can use your fist to gauge the height of the moon above the horizon. And you'll know that you can cover the moon twice just using your pinky. But let's go back to Jupiter for a minute. If you know at a given time that Jupiter will be 25 degrees above the horizon, you can measure that using the pinky-thumb method. But Jupiter appears very small to us, so how do we describe that? In high school geometry, you may have learned about angular measurements, and you'll remember that every degree is broken down into 60 parts called arc minutes, and each arc minute is broken down into 60 parts called arc seconds. So with Jupiter, we say it's 40 arc seconds wide. Planets are always measured in arc seconds, while deep sky objects can be referred to in degrees, arc minutes, or arc seconds in size. To visualize what 1 arc second is, imagine the width of the face of a dime at a distance of 3 miles. That's pretty small. Recently, many observers got to enjoy a visit from comet Tsuchinshan Atlas. The comet was bright for several days when it could be seen with the naked eye, and it was visible in binoculars and telescopes for weeks. Many of the descriptions of the comet would say things like, the coma is 22 arc minutes wide, and the tail is 10 degrees long. Well, by learning the hand method, you can easily imagine what a 10-degree tail would look like, and if you were observing the comet in a telescope, you'd know that the coma would appear a little more than 2/3 the size of the moon, which averages about 30 arc minutes in size. The hand method works really well for most people, and once you learn it, you'll rely on it. One of the first things that people will ask about a telescope is what power is it? Now, magnification is important, but it's not the determining factor in how a telescope is used. F ratio, which is the relationship between the diameter of the primary lens or mirror and the total focal length of the telescope. This is important as faster or lower F numbers are better at viewing wider fields and faint deep sky objects, while telescopes with high F numbers are more adept at narrow field viewing, which makes them excellent for lunar and planetary viewing. The F ratio is found by dividing the focal length of the telescope by the diameter of the primary mirror or objective lens. For example, my C8 has a focal length of 2032 millimeters and has a 203.2 millimeter primary. 2032 divided by 203.2 is 10, so that makes this scope an F10. This is a great F ratio for viewing planets and smaller deep sky objects. Now, my 8-inch Dobsonian has a mirror that's 8 inches wide, or 203.2 millimeters, and it has a focal length of 36 inches, or 914.4 millimeters. Doing the math, 36 divided by 8 is the same as 914.4 divided by 203.2, and we see that this makes it an f4.5 telescope, which makes it a great scope for observing faint deep sky objects, and it can have a wide field of view while doing so. Okay, so now that F ratio is out of the way, let's figure out magnification and the true field of view, meaning how wide a piece of sky are you actually looking at in an angular measurement. It's easy to do, and it is pretty important. I find that when observing, I always start with the eyepiece that gives the lowest power and the widest field. Finding faint fuzzies is much easier to do with a wide field of view. But how do you determine what those numbers are? Thankfully, they're both very easy to calculate. To find the magnification of a given telescope and eyepiece, just divide the focal length of the telescope in millimeters by the focal length of the eyepiece in millimeters, and you get the magnification. Most eyepieces have the focal length printed on them, making this an easy task. For example, a telescope with a 1000 millimeter focal length paired with a 40 millimeter eyepiece will yield a magnification of 25. A 20 millimeter eyepiece would yield a magnification of 50. But how wide is the field of view for these eyepieces? Let's say that the 40 millimeter eyepiece is a Plössl, which has an apparent field of view of 50 degrees. The apparent field of view represents how wide a circle you'd see when viewing through the eyepiece using angular measurement. So to get the true field, we divide the apparent field of view by the magnification, and we get the true field of view in degrees. In this example, the 40 millimeter Plössl has a 50 degree apparent field of view, and we know that it's working at 25 power. So if we divide 50 by 25, we get 2 degrees. Easy. But let's say you're using an ultra-wide field eyepiece with a 100 degree apparent field of view. And in this example, we're working at 50 power. Well, 100 divided by 50 is 2. So now you have a 2 degree field, same as you had before, but you're looking at it at 50 power. So you're looking at the same piece of the sky, but just looking at it with higher magnification because the apparent field of view is wider. That's pretty cool. That's the benefit of ultra-wide field eyepieces, but they can be pretty pricey. So when you're planning an observing session, you can figure out which scope and eyepieces to bring to give you the best views for the objects that you plan to observe. Another concept that can be confusing is the magnitude scale. This actually dates back more than 2,000 years to catalogs made separately by Ptolemy and Hipparchus, where they devised a scale from 1 to 6 to categorize the brightness of stars that they could see. They would simply compare brighter stars to fainter stars to determine the magnitude. It was crude but effective, and the method was used for centuries. Eventually, the magnitude scale got an update, as there are many objects that are brighter than first magnitude stars. Some of these objects are magnitude 0 or even have negative numbers. Objects like the moon, the sun, and several planets and stars fit into this category. The magnitude scale is also used to describe comets, meteors, deep sky objects, and even the brightness of satellites. Today, the magnitude scale is a logarithmic scale, where magnitude 1 is 2.51 times dimmer than magnitude 0. Magnitude 2 is 2.51 times dimmer than magnitude 1, and so on. So using this method, we can calculate that a 6th magnitude star is about 100 times dimmer than a 1st magnitude star. So if there's a 10 magnitude difference, An 11th magnitude star would be about 10,000 times dimmer than a first magnitude star. When you go into the negative numbers, each number represents a value 2.51 times brighter than the previous number. Some examples: Venus can get brighter than magnitude -4, and the Sun is around magnitude -26.5. The faintest stars that most people can see from a pristine dark sky location is magnitude 6.5, which is more than 13 trillion times fainter than the Sun. Wow. With 50mm binoculars under a dark sky, you should be able to see stars down to 3 or 4 magnitudes below your naked eye limit. This is one of the benefits of understanding the magnitude scale. Okay, enough about magnitude. Let's dive into celestial coordinates. As we observe things in the sky, we need a way to describe where they are. You can use altitude and azimuth to describe something where the altitude is the angular measurement from the horizon, and the azimuth represents the degrees on a compass of what direction to look. As the Earth rotates, the stars appear to move from east to west, so their altitude and azimuth are going to be constantly changing. So cataloging objects that way isn't very useful. This is where right ascension and declination, or RA and dec, come into the picture. On a globe of the Earth, you can see lines of latitude and longitude. Those are used to define specific locations here on Earth. For example, the Eiffel Tower is located at 48.8584 degrees north and 2.2945 degrees east. But since the stars appear to be moving slowly across the sky, we use RA and dec as coordinates on the celestial sphere that we look out on. Essentially, RA and dec are analogous to latitude and longitude on Earth. So plus 90 degrees declination is the north celestial pole, which happens to be near the second magnitude star Polaris. Minus 90 degrees declination is the south celestial pole. 0 degrees is the celestial equator. The celestial poles line up perfectly with the Earth's axis of rotation. So if you could observe Polaris over 24 hours, you'd see it make a tiny circle around the pole, while the other stars would make wider and wider circles as they went around the pole. Right ascension is expressed as angular measurement, using hours, minutes, and seconds. But because the lines of RA run north-south, the angular distance from 0 to 1 hours is different depending on your latitude. The RA scale starts at 0 hours and goes to 24 hours, where 0 hours is the point in the sky called the vernal equinox. This is where the sun crosses the celestial equator moving north, what we often refer to as the beginning of spring in the northern hemisphere. The numbers go up, moving east from 0 on the RA scale. Here's an example of giving coordinates for a known object using RA and dec. For M33, the Triangulum galaxy, any catalog will show that it has an RA of 1 hour, 33 minutes, and 50 seconds, and a declination of plus 30 degrees, 39 minutes, and 37 seconds. So if you're using a telescope with setting circles, or your mount is computer controlled, but you want to observe something not in your mount's database, you can manually enter them. Star charts and planetarium maps will also show right ascension and declination. Again, this takes a little getting used to, but once you get the hang of it, it's easy. Okay, no more confusing numbers for the rest of the episode, I promise. Let's get on to something a bit more practical. Many beginners will often ask, how can I learn more about this? With this representing anything telescope or astronomy related. The best answer to this question, in my opinion, is find your local astronomy club. The members will be happy to answer any questions you may have, and you'll be able to hear short lectures about astronomy, and if it's clear, even be able to look through telescopes. I was fortunate to have grown up just a few blocks away from a college campus that has an observatory that's operated by the local astronomy club. The people there are really interested in astronomy, and they want to learn more about it while informing others about just how amazing astronomy is. And every astronomy club that I've ever been a member of has always been very welcoming to beginners to help them get started in their journey. Even in a small state like New Jersey, there are more than a dozen astronomy clubs that have observatories and are open to the public for viewing and presentations on a scheduled basis. But what if you don't have a club near you? Well, there are literally tons of books and magazines about astronomy and astro gear, and there's even more online. Local libraries are a great resource. They'll often have a lot of material on astronomy. Some libraries even have loaner telescopes. The resources online are endless, but I'm going to give you some of the ones that I use the most when planning observing or imaging sessions, or if I just need an answer to something. Stellarium is a free open-source planetarium software package. It's easy to use and has many great features. I'll sometimes just scan around in Stellarium, looking for targets that I might want to see. It's also excellent for learning the constellations. It runs as a standalone app on your computer, or you can run a web-based version that has less features, but you won't be downloading any software. It's also available as a downloadable app for your phone or tablet. Another app that has similar features as Stellarium, but includes some other features as well that can be very helpful tools, is called Mobile Observatory. I use this one on my phone a lot. If you're a planetary observer, you'll enjoy the Jupiter and Saturn moon finders that are built into Mobile Observatory. If you're going to be imaging or observing, you're going to want to know the weather forecast. I've found Weather Underground to be pretty accurate, and their map features let you see satellite imagery for where you are. The Clear Sky Clock, which is found at cleardarksky.com, can provide local weather info as well as seeing forecasts and more. It also lets you search for locations near you that have weather stations. There are several great sites that are useful for planning your sessions, but my go-to is theskylive.com. It's a great website for getting information on many different objects, and it's especially great for comet information. Telescopium.com is useful for planning, imaging, or observing sessions. You want to create a free account there so you can save your settings and gear. Once you log in, you can put in your location and use their search tools to see what objects will be visible at a specific location and time. The Toolbox has a telescope simulator that's great for planning how to frame an astrophoto. You can enter your telescope and eyepiece specifications into the simulator, and it will show how a given field will appear with that setup. You can even save multiple telescopes and eyepieces. It has similar features for cameras as well. It's a really useful tool. Another website that I go to often is cloudynights.com. This is another free website that you can subscribe to. There are forums that cover many different topics. You can read the posts and the comments and find some great information. Of course, you can post your own questions and the comments will roll in with many answers. Their classified section is a great place to buy and sell used astronomy gear. I've bought and sold many times on Cloudy Nights, and it's always been a great experience. Hopefully you're watching this on YouTube. Well, YouTube is an excellent resource for astronomy. There are great channels like the Astro Guy podcast, and there are hundreds of other ones from all around the world. I've personally learned a great deal when I got back into astrophotography just by watching tutorials on YouTube. There are even some excellent videos about many of the apps and tools that we've discussed in this episode. I hope that this has enhanced your knowledge, no matter where you are in your astronomical journey. Hopefully, these ideas, concepts, and tools that we've explored will be helpful to you. Well, that's all for this episode. Thank you so much for joining us, and I hope that you found our time together to be fun and helpful. If you have questions or episode suggestions, please email us at astroguypodcast@gmail.com or leave us a text or a voicemail at 973-404-0380. If you're not already a member, please join the Astro Guy Podcast group on Facebook. You can also visit our YouTube channel, the Astro Guy Podcast, for past episodes and other surprises. Please do all the podcast YouTube things, such as like, subscribe, comment, and share. It really, really, really helps us. If you'd like to help support the Astro Guy Podcast and YouTube channel, you can buy us a cup of coffee. The money is used to maintain and update the equipment that we use to create and publish the show. The link is in the show notes. Thank you again for joining us, and may your skies be clear. As always, Carpe Noctem, seize the night.
I'm Wayne Zool, and this was the Astro Guy Podcast. Thank you for listening. As always, your questions, comments, and suggestions are welcome. Keep wondering. Keep your eyes on the sky. Have fun. Carpe Noctem. seize the night.